Good morning. I am Pratyusha Chowdari, Assistant Professor of GRIT. In this video, I want to discuss adders and subtractors. Adders have very important role in digital relay circuits. In many computers and other kind of processors, adders are used as ALUs, arithmetic logic units. Here are certain examples for adders and subtractors as well. Adders, we are going to discuss half adder, full adder. Under subtractors, we are going to discuss half subtractor and full subtractor. First, it is half adder. Half adder is a combinational arithmetic circuit that adds two numbers and produces a sum bit and carry bit. So, half adder is going to add two bits from A and B and going to produce sum and carry bits. Here we will see the truth table 0, 0 for A and B, 0, 0 for A and B. If I add 0 and 0, sum is equal to 0 and carry is equal to 0. Then second case 0, 1. If A is equal to 0 and B is equal to 1, 0 plus 1, sum is equal to 1, then there is no carry at all. Next, third combination, that is 1, 0. A is equal to 1 and B is equal to 0. If I add these two bits, sum 1 and carry is equal to 0. Last combination 1 and 1. A is equal to 1 and B is equal to 1. If I add 1 and 1, in a normal scenario, the answer is going to be 2. In a decimal scenario, it is 2. So even in binary also it is 2, but we represent 2 in binary as 1, 0. So sum is equal to 0 and carry is equal to 1. Carry is equal to 1. Here I have a K-map for sum and carry. A0, B0, my sum is equal to 0. Okay, A bar, B bar, sum is equal to 0. So I don't represent it. And then 1, 1, my sum is also 0. So A1, B1, my sum is also 0. And sum bit is equal to 1 for two cases. That is A bar, B and A, B bar. So A bar, B is equal to 1 and A, B bar, I have my sum bits are 1. See, there is no grouping formed here, so that the individual terms that we are going to take and we are going to add. Under SOP, these groups are considered as product terms and we'll add them. We will sum them. Product terms are summed together, called as SOP. So it is A bar B plus A B bar, which is expression for A XOR B. So my sum is equal to A XOR B. Next, coming to carry, if you see the carry column, carry is equal to 1 for 1, 1 case. A is equal to 1 and B is equal to 1. The carry bit is equal to 1. So this cell value is A dot B. So carry is equal to A dot B. That is AND gate. So this is the logic diagram for AND gate, sorry, of half adder. So A, B are XORed to get sum and A, B are ANDed to get carry. Next, full adder. Full adder is a combinational arithmetic circuit that adds three binary bits. They are generally A, B and the carry from the previous circuit. So here we are going to take that as A, B, C, and the same two outputs are going to be generated even from using full adder, that is sum and carry out. It is a truth table of full adder. Let's verify the functionality of this full adder by using the individual bits. First case, A0, B0 and C is also 0. 0, 0, 0 case, sum 0, carry is equal to 0. And second case 0, 0, 1, 0, 0, 1 case. So it is very clear that sum is equal to 1 and carry is equal to 0. You have to remember a very small thing over here. If you have number of bits as 1, then sum is equal to 1 and carry is equal to 0. And try to recollect half adder where you have two ones for last case 1, 1. When you have two ones, sum is equal to 0 and carry is equal to 1. The examples are here. 1, 1. When you have two 1, 1s, sum is equal to 0, carry is equal to 1. When you have two 1, 1, sum is equal to 0 and carry is equal to 1. 1, 1, 2, 1, sum 0, carry 1. Okay. And the remaining cases here, see, this case you have C is equal to 1. Here B is equal to 1. A is equal to 1. In these three cases, you have only 1, 1 in the input combination. So sum is equal to 1 and carry is equal to 0. That means 0 plus 0 plus 1. In any way, the answer is equal to 1. So there is no carry at all. Whereas when you have two ones, like the cases here, 1, 2, 3, When you have two ones in the input stream, then 1 plus 1 answer is 2. So in binary it is 1 0. So sum is equal to 0 and carry is equal to 1. Next last case 1 1 1. When you have three ones, the answer is supposed to be 3 in decimal, even 3 in binary. So 1 plus 1 plus 1 in binary is 3, that is represented using the binary bits 1 and 1. So when you add three ones, sum is equal to 1 and carry is also 1. So 3 in binary is represented as 1 1. We know how to weight it is 1 into 2 power 0, 1 into 2 power 1. So 1 into 2 power 0 plus 1 into 2 power 1. So 2 plus 1 is 3. So in binary we represent this way only. So this is the truth table of full adder. Just now we have verified the functionality. See, when you have only 1 1, sum is equal to 1. See, 1 2 3. These three cases my sum is equal to 1. Whereas when I have two ones, 1 2, these three cases my carry is equal to 1. And for the last case 1 1 1, sum 1 and carry 1. Okay. Now we are going to represent the same using K-maps to get the expressions. So this is for carry out. This is for carry out. You have to represent the cell values with the corresponding bit values. 0 0. See, 0 0 0 0 0 0 0 0. Value is 0. Next 0 0 1 0 0 1. Carry out is equal to 0. Next 0 1 0 0 1 0 is here. It is also 0. Next 0 1 1. See this case 0 1 1. A is equal to 0, B is equal to 1, C is equal to 1. It is equal to 1. So A 0, B, C in R 1 1. So it is equal to 1. Respectively, we'll put all the values here, and we have to form the maximum combinational group. Here, this is one group, second group, and third group. So there are three groups. So we'll have three product terms here. They are AB, ACN, and BCN. So this is the formula of expression for C out. And for sum, you represent the same way. There is no combinations at all. So my sum expression is A bar B bar C in plus A bar B C in plus A B bar C in bar plus A B C. So if I simplify the expression, it is A XOR B XOR C or C in. So this is the logic diagram for full adder. Sum is equal to A XOR B XOR C, and carry out is equal to AB, that is first AND gate. Then here it is A C in bar, third one A C in bar, B C in bar is from this. So all these three product terms are summed together to get carry out. Next is half subtractor. Half subtractor is a combinational arithmetic circuit that adds two binary bits. That is A minus B is going to be performed over here. A minus B. Okay. A minus B. So 0 minus 0. If you subtract 0 minus 0, the difference is 0 and borrow is 0. I'm going to explain 0 1 case little later. We just complete the remaining two. 1 0 case. 1 0 case. 1 minus 0. 1 minus 0. If you subtract 0 from 1, the difference is 1 and borrow is equal to, you don't require a borrow, okay? Then 1 minus 1, 1 minus 1, 1 minus 1. So difference is equal to 0 and you don't need a borrow. So this is clear. The second case, that is A is equal to 0 and B is equal to 1. This you have to be very cautious. So 0 minus 1. So you cannot subtract 1 from 0, isn't it? So you need a borrow. So when you take a borrow, so when you give a borrow, what happens? This becomes 1 0. Okay, isn't it? In decimal, we generally do like that. Say for example, if you have okay, here itself I'm going to use. If you have a 56 minus say 9, 56 minus 9. You cannot subtract 9 from 6. So you have to give a borrow from 5. So this becomes 4 and 6 becomes 16, isn't it? This is how we will subtract. Okay, out from 16, you subtract 9 and then you substitute for 4, isn't it? So that is the case with decimal. So here also the same way. What happened? This is 1 0. What happened to text? Yeah. If I give a borrow here, then this becomes 1 0. 1 0 minus 1, when I subtract 1 0 in binary is called 2. It's called 2. 2 minus 1, difference is equal to 1. So you have to remember a very simple point, that is 0 minus 1, 0 minus 1, you have to give a borrow here. Then this becomes 2. 2 minus 1 is equal to 1. So 0 minus 1, difference is equal to 1 and borrow is equal to 1. Oh, and if you observe this truth table, it is very clear that difference is equal. Difference column represents XOR function. So difference difference expression can be derived as A XOR B. Whereas borrow is equal to 1 for the case A0 and B1. A0, B1. So it is simply not A and B. You can also use K-map to derive this. You try to solve this using K-maps. Next, full subtractor. Full subtractor is a logic circuit which is used to subtract the three binary bits. That is A minus B is going to perform by using full subtractor. This is the truth table of subtractor. Let's execute. Let's check all the combinations. A0, B0, C0. I mean B in 0. 0 minus 0, 0 minus 0. Answer is 0, 0. Okay. Next case. A0, B0, B in is equal to 1. When I subtract 0 minus 0, the results are 0, 0, isn't it? And now the difference is equal to 0 after subtracting A minus B. So it's difference 0. So here the difference is equal to 0. Here the difference is equal to 0. 0 minus 1. So when you are performing 0 minus 1, you have to take a borrow. So borrow bit becomes 1. Borrow bit becomes 1 in this case. So 1 comes over here. Then this value will become 2. 2 minus 1, difference is equal to 1. Is this clear? Let me clear one more time. I'll explain one more time. 0 minus 0, difference 0 and borrow is also 0. Okay. So initially difference 0 and borrow also 0. So initially difference 0 and borrow also 0. Okay. Then I need to subtract 0 and 1. So that is 1 has to be subtracted from the previous difference, that is 0. Okay. 0 minus 1. In such case, I require a borrow. When I give a borrow to the previous difference that will become 2. 2 minus 1 is equal to 1. Okay. Next, 0 minus 1. It is not possible, isn't it? So you require a borrow. So when you give a borrow here, this becomes 2. 2 minus 1 is 1. So difference is equal to 1 now. 1 minus 0 is equal to 1. That is what is the difference. Next, 0 minus 1, A minus B, 0 minus 1, 0 minus 1. You cannot perform this. So you require a borrow to perform this. So borrow bit becomes 1. So this is 2 now. 2 minus 1 is equal to 1. 2 minus 1 is equal to 1. So 1 minus 1 is equal to 0. Okay. Next, 1, 0, 0. 1 minus B, 1 minus 0 minus 0 is difference is equal to 1 and borrow is equal to 0. Next, A minus B is 1 minus 0 minus 1. 1 minus 0, the difference is equal to 1. So 1 is the difference here. So 1 minus 1 again, difference 0, borrow 0. Next 1, 1, 0. When you subtract 1, 1, the resultant is 0. 0 minus 0 is 0. You don't need a borrow. Next 1 minus 1, 1 minus 1, difference is equal to 0. 1 minus 1 is 0. Okay. 0 minus 1 now. You are performing 0 minus 1 now. When you are subtracting 0 minus 1, you require a borrow. So when you take a borrow, that becomes 2. 2 minus 1 is equal to 1. That is how you can analyze the truth table. And when you substitute the truth table in K-map to get the expressions, difference is equal to A XOR B XOR B in, and borrow is equal to A bar B plus B into Bn. Or you can also split this, A bar B plus A bar B in plus B dot B in. So this is the logic circuit for full subtractor. I hope you are clear with half adder, full adder, half subtractor and full subtractor. Thank you.